Hey everyone. So we talked about limits a little bit. By a little bit, I mean it was a more than 20-minute video. So I talked about limits, and now we're going to talk about some rules for limits. And don't worry, this is going to be a much shorter video than last time. So before we talk about the rules of limits, I just want to establish some terms that we're going to be working with this entire time. To start out with, for all of these rules, let B and C be real numbers. So B and C are real numbers, and N is a positive integer. So this is stated at the outset. So every B and C number that I write, it is a real number. Every N number that I write is a positive integer. So got that out of the way right quick. So let's talk about some properties of limits. So some properties of limits, the best types of limits are when we're finding the limits of what we call well-behaved functions. A function is a well-behaved function if, when you take the limit as x approaches c of the function, it equals the function value at that. Some well-behaved functions that we know are polynomials, rational functions for most of the domain, radical functions for most of the domain. In fact, pretty much all of our 12 basic functions are mostly well-behaved. The only ones that are not really well-behaved are like the greatest integer function. Rational functions technically are not well-behaved, but there are some. Like if you had f of x equal 2 over x squared plus 2. There's no discontinuity in this. There's no value of x that would make that denominator 0. So this is actually a well-behaved function. There's no break in it. There's no discontinuity, so there's no value from negative infinity to infinity that would cause the limit to not just be the function value. So if this works at every value of c for the domain, it's called a well-behaved function. But not every function is a well-behaved function. But just by analysis of the domain, you can tell whether it's going to be well-behaved or not. Now, if it is a well-behaved function, there are some basic ones, some really basic ones. One of them is the constant function. If you just have f of x equals b, it's a horizontal line. And the function value at every point on the horizontal line, regardless what c is just b. So if you have a horizontal line, the limit at every value is the value of that horizontal line. If you're taking the limit of our identity function at c, the y value would be c. So very straightforward. If you took the limit of our most basic power functions, where n is an integer, a positive integer, that's going to be a well-behaved function. Its limit is going to be c to the n. And then even if you do a root function, it's going to be the nth root of c. Now, there is a little caveat. I'm not going to write it out because I don't feel like writing out the whole thing. And you can just listen to my voice and replay this if you need to. But there is a caveat to this. If n is odd, there's no restriction on this. There's no restriction on what c can be. But if n is even, c cannot equal 0. If n is odd, it doesn't matter, because if n is odd, the shape of the curve is going to be like this. If n is even, it does matter because the shape of the curve will be like this. And at 0, you'll be at this point. There is no left-hand limit, so there is no limit when c is 0 there. All right? Cool. So those are just some examples of well-behaved functions, basic well-behaved functions. Now let's talk about some properties. Now, before we talk about properties, the rules that we established before are still in play. B and c are real numbers, n is a positive integer. And we also are going to have two functions, f of x and g of x. And those two functions, for f of x, the limit as x approaches c of f of x, we are going to say is L. Oh, I should say let. And the limit as g of x rather approaches c, as x approaches c of g of x, is going to be k. So b and c are still real numbers, n is a positive integer, and these limits as f of x approaches, as x approaches c for f of x, it approaches L. As x approaches c for g of x, it approaches k. So some basic properties of this. They're pretty straightforward. If you would like to go further in depth, you're more than welcome to come and visit me during the Zoom hour, but I'm not going to go really in depth proving these. They're very basic. The first one is our scalar property. And that says that the limit as x approaches c of b times f of x is b times L. So if you have a scalar times your function, your limit is going to be the scalar times the limit of the function. We also have a sum and difference property. And that's that if you have the limit as x approaches c of the sum of two functions, the limit of the sum, or sum or difference, is the sum or difference of the limits. It also works for products. If you have the limit of a product of functions, it is equal to the product of the limits. Just for posterity's sake, I'm going to make it LK instead of KL. Same with the quotient. But I'm not grouping the product and the quotient together because there is a restriction on the quotient. But if you do the limit of a quotient of functions, it turns out to be the quotient of their limits. So L divided by K, but K cannot equal 0. Because obviously you'd be dividing by 0. And lastly, there is a power property of limits. So if you have f of x to the nth power, it's the same as the limit of f of x to the nth power. So L to the n. So these are just some properties of limits that we can use as we try and evaluate and work with them. All right, have fun. Bye.